Thank you everyone for coming. I know it's kind of late in the day now, so I appreciate this many people showing up. Thank you to the organizers. It's great going back to kind of a smaller single track conference. The Ruby community kind of lost these, and it's nice to be at one again. Here's my contact info. I can't figure out how to customize the title slide, so it's here. So the title of this talk is Making Ruby Faster. And the basic motivation for this talk is the three major Ruby implementations, JRuby, Truffle Ruby, and CRuby or MRI, whatever you want to call it, all have JIT compilers. And over the past few years, representatives from each of the projects have talked extensively about the latest developments in their JIT compilers. But if you come from a coding boot camp, or maybe you're just someone that works in high-level Ruby and writes applications all day, you might not really understand how these JIT compilers work. And consequently, you're missing out on the latest developments in the language. So this talk is intended to be something of a prequel to those other talks. Hopefully we can fill in the knowledge gap there. It's a lot of info to cover in 30 minutes. I'll probably run a little long, but I'm gonna go as quickly as I can. So to start off, we'll look at how CPUs actually run software. So we'll do a really crash course in computer architecture. Then we'll get into what compilers are doing, and then finally, how that pertains to JIT compilers and Ruby in particular. So how software is run on CPUs. If we take your typical laptop or server and kind of just boil it down to its essence, we have two critical components. We have the CPU, or central processing unit, and this is what really does the operations in your computer. And again, I'm simplifying here. There are other things. There's a lot of work being done on GPUs now, but we're working in Ruby, so I'll focus on the common architecture. And then we have another component, which is memory. And this is generally what we think of as RAM or DRAM. And the memory and CPU are connected by something called a bus. And for all practical purposes, that will just be a set of wires. So if the two need to communicate, they need to transmit data over these wires. And there are transmission delays in doing that. On top of that, there are trade-offs in memory that make it slower than the CPU. So the CPU has a set of storage locations built into it called registers. There's a limited number of these, like 16 or 32 total, and they're small. Depending on whether you have a 32-bit or 64-bit processor, they're going to be 4 or 8 bytes each. But they're there, and if we can work with them, they are supremely fast. They're built right in the CPU. They don't need to go over the bus, and the memory technology is just faster. The CPU also has execution units in it. One you might come across is the ALU, or the arithmetic logic unit, and this is what does your mathematic and bit operations, which tends to be the bulk of what a CPU does. So a computer is really quite simple. The CPU doesn't do anything until you feed it instructions. And when we compile a program, what we're doing is encoding it into a set of instructions. And for this, I'm talking like C, Go, or Rust. Ruby operates at a higher level, and we'll get into that. But your program ends up just being a set of instructions. And when you execute the program, the CPU loads it, it puts it in memory, and it tells the CPU where in memory your program is and how to start executing it. And then the CPU will communicate with memory necessarily, because what we're hoping it does is operate on data. Otherwise, it's a closed system and it doesn't do anything useful. So the instructions change per CPU or per CPU family, and they're defined by something called the instruction set architecture, or an ISA. And this really gets into all the tiny details about what your processor can do. So one of the things it might do is explain what the names of your various registers are, how big they are, how you can access them. Are they intended for general use, or do they have special purposes? This is coming from the x86-64 architecture. This one's a little weird because it's been built up progressively over time, and it has backwards compatibility modes. But here we can see that Intel allows you to access registers in 32-bit mode, or in 16-bit mode, or 8-bit mode. And you choose which one you want by using a particular register name. Your ISA will also define the data types the CPU supports and how you represent those in memory. So here, all these are being taken from the Intel architecture guide. It's an incredibly rich resource, and it's surprisingly accessible. So here we can see the integer data types. And then it gives you detailed information on each instruction. So this is an overview for the multiply instruction. I'm not expecting you to be able to read this, but there's a description, and it gives you tables and stuff. Notably, this is for unsigned multiplication. There's a completely different instruction for signed multiplication. and different ones for doing floating point. So you need to understand when you can use which instruction when. Blowing up the table from the previous page, we can see that within the multiply instruction, we can operate it in 8-bit, 16, 32, or 64-bit mode. And this table tells you where the result will end up. So what register will end up with the result of the operation. And with the multiplication instruction, you can actually end up with the value split over 2 registers, which is why the bottom 2 rows have a colon there. But to really help you understand it, it even comes with pseudocode that tells you how to interpret that previous table. These are really helpful resources. But while we have these instructions, the CPU doesn't know how to basically operate those. We need to encode it into binary. So the ISA also comes with something called an opcode table. And this tells you how to encode each of the different forms of the instruction. So while there is one mul instruction, whether you multiply a register by a register or register by a constant value, they get encoded as 2 different instructions. So the opcode table tells you exactly how to represent that in binary. You could actually sit there and do this by hand if you wanted to. It's incredibly tedious, but there's nothing magical going on. When you load that into memory and the CPU processes it, all it does is read it and decode it according to the opcode table. If you've heard of ISAs, you might have come across the terms CISC and RISC. So CISC is the complex instruction set. This is, at one point there was a debate over which one was superior. For the most part, RISC is one, but because the Intel and AMD instructions have carried forward so long, we have almost all certainly interacted with a complex instruction set computer. But RISC, like I said, is pretty much what's one. So it's what Apple's using. It's pretty much what all your mobile CPUs use. It's being adopted more aggressively in the server space. And the key differences are how complex the instructions are. I know that seems a bit glib, but in a RISC architecture, the instructions are just simpler. They take up the same amount of memory, and they take up the same number of arguments. With CISC, at some point, they were trying to have like compressed instructions. So a given instruction can be represented in a variable number of bytes, or an instruction might be doing multiple things. The other implication of this is that RISC machines tend to have more registers, and you can use them more freely. We saw already with that multiply instruction on the Intel set, you don't get to determine where the result goes. It's just going in those registers. Regardless of ISA, we have some special registers. And these can be conceptual, but oftentimes they're actual registers. One is called the program counter. Sometimes it's called an instruction pointer or an instruction register. And this is the register that holds the address of the next instruction to execute. So generally, when you're running a program, it just gets incremented. So the CPU runs the next instruction in memory. But if you make a function call, or maybe you have an if-else statement and you need to go to the else block, then you would jump by setting a new address in that register. Then we have the stack pointer. The stack is a special way we treat some memory. So this will just be in RAM, but unlike what you might do with malloc, where you allocate data on the heap and you get back a fixed chunk of memory, and you do whatever you want with it, and then you free it, the stack follows the stack data structure. So we're going to push and pop values out of it. It's an extremely efficient way to work with data, but there are limitations on it. And for all intents and purposes, the stack can grow unbounded. Realistically, you might run into something called a stack overflow, and that's precisely what's happening. You've grown the stack too much. Kind of going with that, we have the frame pointer. So when you represent a function in these instructions, you tend to work with the stack because it's easy and it's fast. But each function will have to modify the stack. So if you make a function call and then it returns, the stack pointer needs to be reset to the correct position. So the frame pointer is just a little helper that allows each function to know what the previous value of the stack pointer was. All right, so now we can get into what compilers are doing. The output of encoding according to that opcode table is something we call machine code or native code. And again, these are binary values. If you've ever seen an executable called a binary, that is why. As I said, you could handwrite this if you want to. With the general computing architectures we use, it would be really hard. Like on a 64-bit CPU, you're specifying all 64 bits. But on simpler 8-bit microcontrollers, you might need to. But for all practical purposes, the lowest level anyone really works at is something called assembly language. So this is a programming language. It is written in text, but it has like almost a one-to-one correlation to the instructions from the ISA. So the assembly language changes depending on which processor family you run on. But there is a common syntax across them. I think assembly gets kind of a bad rap as being really complex. It's actually an incredibly simple language. There's not a whole lot you can do. The complexity comes from the fact that you have to think of how to break up a logical process into discrete steps for the CPU to perform. And again, like you need to keep track of whether you're doing a signed multiplication or an unsigned. But if you're just looking at a snippet of assembly or you want to try to play with this on your own, you could probably learn it in a day or two and write functional code. We take that ASM source code, feed it into something called assembler, and out pops machine code. There's usually something called a linker that comes into play here, but we'll skip over that. If you've ever heard of disassembly or a disassembler, that's just doing the process in reverse. If you have an executable given to you, like maybe you bought it from a third party, and they didn't give you the source code, you still have the set of instructions necessary to perform that computation. So this is where reverse engineering comes in. People use disassemblers and what you can decode according to that opcode table and get back some assembly. Won't be the same, you won't have the comments and things like that, but that's what's going on there. But we tend to not even work at the assembly level, we work with compilers. And again, for the most part, I'm still talking about like GCC or Clang or the Go compiler. So we have a high-level language and we feed it into another program called a compiler and it outputs a program in another language. In our case, that language is machine code. Sometimes it emits assembly and then invokes the assembler, but that's an implementation detail. But all a compiler is a program that takes another program as input and outputs a new program. And we do have high-level compilers that go from one language like TypeScript to something like JavaScript. And sometimes we call those transpilers, but they're fundamentally the same process. And so for the rest of this, we will focus on generating machine code. All right, so by way of code example, we will look at some C. So this is doing a 32-bit integer addition. If you're not familiar with C, the int is just a 32-bit integer value, and we have to declare the parameter types as well as the return value. And if we compile it to assembly, we get these 10 lines. It looks overwhelming, but once you kind of understand what's going on, it's not that hard. I've rewritten it in Ruby, so you can see it side by side, and it's pretty messy because the state in Ruby is global. And that's because it is in the CPU. The registers are shared, they're global. The stack is going to be global. But if we break the assembly apart, we can see on line 1, we have this thing that matches the name of the function. And this is going to be called a label. This is purely an assembly construct. It allows us to give a name to a particular location in the instructions. So we can now jump or call to these labels. There's a ret instruction, and this helps you implement functions. And what it does is it restores the value of the instruction pointer to what it should have been to resume execution after your function call completes. And then there's an add instruction. So this is adding on 2 registers. As long as we get those values A and B into those registers, we can do the addition. The rest of the code is there for something called an application binary interface, or an ABI. Unfortunately, ABI is a bit of a loaded term because there's different situations where you could have different binary interfaces. But for this one, we're talking about what the ISA and the platform agree upon. So the reason we use this is when you write assembly, you have full control over the computer. You can do whatever you want with registers, you can do whatever you want with the stack. But if you want to coordinate with an ecosystem, then there needs to be some kind of agreed upon protocol, and that's what the ABI is. So a lot of the steps in that previous function were there to coordinate with the debugger. The debugger needs to be able to find where the arguments to that function are, or where it is in the stack, so we can step into method calls. This also comes up if you want to call code in a shared library. If someone compiles a library in C, and I want to dynamically load it and call it, we have to agree upon how I can call it. So we have to agree on where the arguments to that function appear, and we have to agree upon where the return value is. Likewise, because we're both sharing the same set of limited registers, we have to agree upon who can modify what. So we split the registers up into 3 classes. One is called caller saved, which means if I, as the code calling a function, need a particular register in that set, I'm responsible for backing up and restoring it. And then we have the inverse, which is callee saved. So if you call a function and it wants to use one of those registers, then it needs to back it up and restore it. But if either case you don't need the registers, then you can no-op the whole thing. And then we have scratch registers. These are like just temporary variables. There's no guarantee about whether a value will be there across a function call. So if we go back to that assembly, all of this is just to work with the debugger. And if we don't want our application to be debuggable, we can remove it. Here's the same assembly for the same function, sorry. Here's the ARM64 assembly for the same function, just by way of example. If we look at them side by side, you can see some of the differences in CISC versus RISC. So in the Intel AMD side, we use a move instruction for putting values into memory and reading them back out, whereas in ARM, there's separate load and store instructions for that. And we can see the difference in complexity with that add instruction. Just like the multiply instruction we saw before, the add instruction on Intel will put the result in the EAX register. So we only use 2 registers as arguments here, whereas on the ARM side, we get to say where the response will go, so we pass 3 arguments. I mean, the compiler took care of some stuff for us that would be tedious to do otherwise, but the real benefit of a compiler is that it can optimize our code. It can produce a semantically equivalent program that runs more efficiently. In certain limited circumstances, you probably could write more efficient assembly code because you have more domain knowledge, but a compiler can apply a rigorous set of optimizations and will generally outperform what you can handwrite. So for instance, if you have C code that you never actually call, then the compiler can see that and just not generate machine code for it. Or if within a function you are recalculating the value multiple times, the compiler can detect that, calculate it once, and then use it for you. It can even eliminate the overhead of doing function calls by doing something called inlining, where it literally takes the body of one function and just like copies and pastes it into the thing that would be calling it. We can remove the debugger support, so that's a flag you can pass directly to the compiler. And for the most part, we don't ship with debugger support. For most end users, that's not something that's valuable, and it adds overhead to each of the calls. And then finally, the compiler can help you manage the registers. Because remember, there's only like 16, maybe 32 of them, depending on the ISA, and you want to avoid a process called spilling. And this is where you need a particular register, but it's already in use. So you have to copy it to memory, go over that relatively slow bus, then use the register, and then restore the value later. So the compiler can adapt to changes in your code and figure out which registers aren't being used yet and try to use those for particular operations. Or it can do a register-to-register move, which will be way faster than going out to memory. So if we run the code, the compiler again, and enable optimizations, that assembly gets really much shorter. We're down to 3 lines, and it's basically just the addition instruction with the return. Interestingly, on the Intel side, the add instruction got replaced with something new. This LEA instruction is supposed to be used for loading addresses, but it is a handy way of doing addition, and the compiler takes advantage of that. So that's not something you probably would have written by hand, but the compiler can do it for you. To see all this output, I use a tool called the Compiler Explorer. It's available at godbolt.org. It's a really cool system. You can basically give it language, code snippets in different languages, and then see the generated assembly. So this is a great way if you want to try to better understand how all this works. All right, so that leads us into JIT compilers in Ruby. So up until now, we've been talking about ahead-of-time compilers, or AOT compilers. So this is a situation where we need to compile the entire application before we can execute it. So with like C, Go, or Rust, Zig, what have you, you can't just run that code. You need to compile the whole thing. With Ruby, we can do something called JIT compilation. And that's because Ruby runs on a virtual machine. This is a fancy way of basically just saying it's a fake computer. So we build up a machine that logically functions like a computer, but eliminates any of the differences in the various ISAs. So if there is a virtual machine implementation for a particular processor family, then your Ruby code will run the same on it. And this is why you can write code on like an Apple MacBook laptop and still run it in a Linux server in production without having to do any additional code changes. And the virtual machine will provide some facilities like memory management, so we don't have to do that at the low level. But our Ruby code turns into something that can run on that. And we say in this case that the code is interpreted. So whereas we were saying instructions are executed, here we're saying the Ruby code gets interpreted. And that happens in something called the interpreter. So this is a subsystem of the virtual machine. Now, generally when we build compilers, they're done as a pipeline. And I just don't have time to get into all that. But one step is a thing called a parser. And what it does is it takes your high-level Ruby code and turns it into something that the computer can more easily work with. Things like comments and white space and punctuation just have no semantic meaning in the language, and they make it complex if you were trying to operate directly on that. So the parser will turn the code into either an abstract syntax tree or bytecode, and we can have AST interpreters or bytecode interpreters. In C Ruby, the one that you most likely use, the bytecode is something called yarv. By way of example, this is some of the AST output. I don't expect you to read it, but you can see that it looks nothing like Ruby code. This is a tree structure, and you might be able to understand why it's easier for an application to iterate over and execute this. The yarv instruction set is something you can actually play with if you want. So C Ruby comes with this -- dump instruction, and you can give it different arguments that impact how it'll process code. So here we have a very simple inline addition function, and we can see in the output that it's generating a send instruction. So this will be a particular instruction in the yarv bytecode that is responsible for invoking methods. But just like GCC and friends can optimize C code, the yarv compiler can optimize Ruby code. So here I'm running the dump output with a different flag, and what we can see is that the send call was replaced with a specialized instruction for doing addition. So this is also an interesting aspect of virtual machines compared to traditional ISAs. We can grow the instruction set relatively cheaply. With an ISA, to add a new instruction, you have to build a new piece of silicon. It's wildly complicated, but with the virtual machine, we have more flexibility. Now, we don't want to keep adding instructions because eventually they don't pay off, but here's a situation where the Ruby core team determined being able to do an addition without going through a general method call would be advantageous. So another part of the VM is something called a profiler. If you've ever done performance analysis of an application, you might have used something called a profiler. It's a tool that instruments your code and tells you how frequently certain pieces of it get executed, how much time is spent in it, and that helps you figure out where to direct optimization efforts. But the VM, or at least the ones that have JIT compilers, so again, C Ruby, Truffle Ruby, and JRuby, they have a profiler that operates internally, and it, as it's interpreting your code, takes measurements. So it can do things like measure how frequently a particular function is called or how many times a loop is iterated through. It can watch the values flowing through the system. And it'll have its own internal heuristics and thresholds that it uses to determine when code becomes hot. And at that point, it submits it for compilation with the JIT compiler. So the JIT compiler is conceptually quite similar to the AOT compiler. It is going to emit machine code that we can execute. And that code gets stored into a special region of memory we call the code cache. So generally, we bound the code cache because we could keep JIT compiling things. In C Ruby, you're able to garbage collect the code cache. Sometimes you JIT compile code that you no longer need, and it's worthwhile to expunge it. But if you've ever seen the term code cache, that's all it is. It's just a region where the JIT compiler stores machine code. Whereas an AOT compiler will compile your entire application, and it does different scopes and involves the linker to help with that. In a JIT compiler, we compile a much smaller piece of code. So there's one thing called a basic block, and this is kind of an internal way of representing code. And the YJIT compiler operates with basic blocks. It's sometimes called straight line code. So if we were to just look at a method, anytime you execute an instruction all the way up until you branch, which would mean making another function call or having like an if-else or a ternary operator, all those parts that don't need to jump around group together in something called a basic block. And a compiler can optimize that code very well because it knows nothing else is executing in between. A bit more frequently used, and what TruffleRuby uses, and JRuby does as well, is a method level compilation scope. So this will compile an entire Ruby method. And then you might see something called a trace compiler, where this actually measures the way your code flows through multiple functions and compiles just the parts you need there. To the best of my knowledge, there aren't any tracing JIT compilers in use in Ruby right now. There was one called Topaz at one point, but I don't think it's actively developed. But once the JIT compiler generates its machine code and stores in the code cache, it updates its own internal state. So now when you call that Ruby function, instead of taking you to that part of the interpreter to execute it, it jumps over into the machine code. So what's also interesting about JIT compilers and where it gets really compelling for Ruby is we can do speculative optimization. So if we take this very simple example in Ruby, what does the function do? Well, if A and B are integers, it does integer addition. If they're strings, it does string concatenation. If you give it arrays, it will append them. You can't know ahead of time what that function is going to do. Sorry, reset. So if you attempted to do an ahead of time compilation on this, you would have to be very conservative about it because you don't know what it would do. But the JIT compiler, with its profiler, has been measuring how your actual application uses it. So it can do speculative optimization. It can speculate or guess that you will continue to run code in a consistent manner, that you've approached something called a steady state. And it can update its own internal representation, whether it's the AST or the bytecode, to optimize even further. Now, it does need to be able to handle the case where its assumption isn't held, and it'll set up a fail-safe for that to allow it to recover. So by way of example, I want to look at one really particular optimization that helps Ruby quite a bit, and that's method lookup. So if you're not aware, just about everything in Ruby is a method call. When you use that plus operator, that is a method. It's not an overloaded operator. You can define it in multiple classes. A lot of the things that look like keywords are actually method calls as well. And every time you want to execute a method, we need to look up its function body someplace. And this gets even more complicated in Ruby because it's highly dynamic. We can define new methods at runtime. We can edit the definitions of an existing method. We could even mess with the inheritance hierarchy using things like module prepend. And every one of these things can impact the result you would get from a method lookup. So the conservative thing to do is to just do the full lookup all the time. But that is an expensive operation. So we introduce caching. Now this all happens inside the VM. You shouldn't be aware of it unless there's a pathological performance case. So the simplest cache we have is something called the global method cache. And you can think of this as just a hash table where the key is a combo of the class name and the method you want to look up, and the value will be the function pointer, so the spot in the interpreter where that function is implemented. If we have a cache miss, we need to go do the full VM lookup to find the method, and then we'll populate it. We have to be very careful to invalidate this cache at the appropriate point, though. So early on, when CRuby had the global method cache, it would be really conservative in the way it invalidated things. If you modify the class at all, it expunged all of the cached methods in it. Nowadays, we can invalidate more granularly, but it's something you need to watch out for, because otherwise you could invoke the wrong method, and that would be really tricky to debug. For practical considerations, this global method cache is bound. Usually it's like 2,048 entries. You can configure that, but if you go too far, then the lookup isn't as fast and the cache isn't as useful. So we have to evict values as the application's execution evolves. Usually we use a least recently used policy to eject values. But where you really got to be careful is there's only 2,048 entries. If you're running code in a loop that uses more methods than that, then you're going to keep round robining through the cache, and you don't end up really benefiting from the fast lookup. So the solution to all caching problems is to add another level. And that brings us to something you might have heard of called an inline cache. This gets brought up quite a bit in various Ruby optimization talks. This is an old VM optimization that comes from Self and Smalltalk, and it's actually really simple, even though the name sounds kind of funky. So what we're going to do is, instead of just having that global method cache, we're going to cache at a call site. A call site is just like a fancy way of saying where you call a method from. So if we take that add method we had before and we call it from 3 different places, each of those locations is a different call site. As a speculative optimization, we need to ensure that our cache can recover if our speculations fail. But as long as they hold, we can use the cache. And if they don't, then we just transition the state. So these inline caches use almost kind of scary terms. They start off in an uninitialized state, so we just haven't seen anything. The first time we see a value, we say it's monomorphic now, which is just a way of saying it has one form. Now, if we see the same values or types of values come through, we can just keep using that monomorphic cache. If we see a new type, we then transition to polymorphic, which just means multiple types or multiple forms. But at some point, we may decide we don't want to keep adding entries because at that point, it's not advantageous. We're having like a chain of else statements, and we have to add values in memory for each of these caches. When that happens, we call it megamorphic, and we just say, look, we're going to give up trying to cache this at all. You could go from monomorphic straight to megamorphic if in a particular spot you don't want it to be polymorphic, but you don't need to get hung up on that. By way of example, we'll go back to our friendly add function, and here we're going to use 2 integers. Now, internally to the VM, where it is now interpreting using its internal representation, it will replace the body of that addition function with something like this. There's some simplification going on to make this look nicer in Ruby, but basically it sets up a guard, and that guard is going to check that the class type matches what we expect and that the class hasn't changed in such a way that the cached method would be invalid. So here we're going to set up a type guard to make sure A and B are still integers, and if they are, we can use a cached lookup directly on that plus operator from the integer class and then make the method call. If it doesn't, then we need to transition the cache. So now we'll call it again with 2 strings, and all we do is add another set of else ifs. So it's not really that hard. And again, this all happens behind the scenes for you. This is one of the ways the VM optimizes your code. Now, here we're going to do quite a few of them. So keep in mind, 5, 6, 7, and 8 are all different call sites. But the plus operator, the thing we're looking up on line 2, is one call site. So it's seeing different values coming through it. In this case, we're going to say, like, it's too chaotic. We don't know if it's going to continue to change. So we're going to give up trying to cache. We'll just do the full VM lookup. Using some additional state, we might still go through the global method cache, but we don't want to blow that out. So the VM will track whether it should use it or not. Now, this is all happening inside the interpreter. But that code is something that we can JIT compile, even though you've never seen it. It's all hanging out inside the VM. And that's where things get really interesting, because let's say the case where we've only seen integers, we can compile a code that looks like this. And we're seeing our friendly add instruction from assembly. So this code runs basically as quickly as it does on C. There's a few things in here where we need to do like compares to make sure that the class matches what we like, but compares are really cheap inside assembly, so that's fine. And if our assumptions don't hold, we'll do the process of de-optimization. So this allows us to recover from bad guesses. That's it. It sounds like a big word, but all it does is it takes our jitted code and throws it away and tells the interpreter to go back to interpreting the code. It's actually a pretty complex process because we need to make sure that when we transfer back to the interpreter, we don't execute something we've already executed, but the VM handles all that for you. And this is one of the ways that we make method calls in Ruby actually work well. There's other things that RubyJIT can do for us. In Truffle Ruby, all of our core library is written in Ruby. So we can do Ruby method inlining, just like we talked about doing with C. So on lines 1 through 6, we can see how the empty method in array is implemented. And this is how it's actually implemented in Truffle Ruby. So now anywhere we use that empty method, we could potentially inline it. So lines 9 to 11 shows a blank function like you might see in Rails, and it checks if the array is empty. This could actually be used with multiple types, but because we have those inline caches, if we only give it arrays, then we can speculate that we will continue to see arrays, and when we inline it, we can eliminate the empty call entirely by replacing it with its body, which is what we see on line 15. That doesn't seem like much, but it avoids all the complexity of doing the method lookup and caching that we had previous. And these things have a snowball effect. So maybe now the compiler can see it's even simpler and continue to inline and use something called constant folding. This is something that we can't do in C Ruby yet because the core library there is written in C, and it's incredibly difficult to take some C code that was ahead of time compiled to machine code and try to inline that into Ruby. Another cool little optimization that JIT compilers can do for us is something called escape analysis. So it's kind of convenient in Ruby to use like array literals for some things. So here we want to check if a value is the minimum. It's kind of contrived, but I've seen quite a bit to get the min value, create this array, and then call min on it. This array is never returned. It doesn't get passed to any other function, so it doesn't escape. It stays within this method that we're compiling. And the JIT compiler can go, okay, well then we don't actually need the array. We can eliminate the allocation and perform the operation, but you don't pay the overhead of allocating that object. And I think C Ruby just added some YARV instructions to do something similar, so that'll work in the interpreter as well. Another thing that JIT compiler can do for us is eliminate the overhead of metaprogramming. So metaprogramming is this amazing facility that allows us to do some really cool stuff. It's what makes Rails so easy to work with, but the conventional wisdom holds that that comes at some kind of performance penalty, some amount of overhead, but a JIT compiler basically gets rid of it. So we look at the send instruction. Because we can have an inline cache on the send method, if we continuously give it the same function name, then we can speculate it's the same, and that code will compile to be exactly the same with the addition of those guards. Likewise, we can do the same thing with method missing. So Rails has this cool feature where I think in active record, if you use one of the helpers, it will call define method, so the next time it doesn't have to go through method missing. Truffle Ruby does that everywhere, so all your Ruby code gets that cool optimization and you don't have to do anything. And then another one is respond to. Again, using inline caches, we can basically turn that into a constant. And then if you have like instance variable get and set, the JIT compiler can eliminate the method call entirely and basically just do a field lookup, which is extremely efficient and really what you would expect just reading a value like out of a struct in C. There's plenty of room for more work in Ruby JIT compilers, but that's where we're getting started. So hopefully this helped. JIT compilers are conceptually quite simple. They just take your Ruby code and then internally make it better. And then they send it over and make it into efficient machine code. So this allows you to make Ruby that runs as fast as C in cases without having, as an application developer, to try to come up with clever hacks around the VM. The JIT compiler will be faster than interpreting, but we have this phase we call warm-up. We have to start running in the interpreter so we can profile it, but then most applications reach something we call steady state. They end up in some kind of hot loop where they're executing the same code over and over. If you think of a Rails application, you do a whole bunch of things to boot the application up, but then you have a limited number of controllers, and you basically run the same code forever. And then when that happens, we hit peak performance. The JIT compilers can optimize based on values flowing through your program. So this means that you and me could end up with two completely different sets of machine code. It allows the interpreter and the compiler to build code that runs efficiently for the way you actually use an application. And this is a big difference than what you see with like C or Go or Rust. They don't know how your application runs, so they can't do those speculative optimizations in advance. There's ways of providing runtime profile data, and in that case, it can try to reorganize things to be more efficient, but whereas with the JIT compiler, we can always go back to the interpreter, so we don't have to compile the stuff we're not using. With an ahead-of-time compiler, you can't go back to the C source and compile it again, so it needs to have all that data in there. So in cases, we can actually generate code that would be more efficient than if you tried to have it of equivalent expressivity in a language like C. And these JIT compilers work best with idiomatic Ruby code. Unfortunately, there's a lot of like clever hacks out there for exploiting particular implementation details of like C Ruby. Those things don't optimize very well in a JIT compiler. Likewise, just jumping to native extensions for your code, while that runs really quickly in the interpreter, it limits what the JIT compiler can do and can ultimately become a barrier to your performance. So I'm hoping as a community we can start moving away from that sort of stuff and embrace the JIT world and end up with more efficient code as a result. This is just a slide with some resources if you're interested in more things, and thank you for your time.